Dr. Adrià Gómez-Valent here today. Thanks a lot for accepting our invitation. Dr. Gómez-Valent is a junior leader postdoctoral fellow at the Institute of Cosmos Sciences at the University of Barcelona, working on the project looking for concordance in cosmology through model-independent assessment of data consistency and the exploration of physics beyond lambda CDM. He obtained his PhD at the same institute in 2017 under the supervision of Professor Joan Sola Berquela, working on vacuum energy in quantum field theory and cosmology. Adrià has had postdoctoral positions at the Institute for Theoretical Physics in Heidelberg with Professor Luca Mendola and University of Rome Tor Vergata, including several research visits to the University Federico II of Naples and the Institute of Cosmology and Gravitation in Portsmouth. Today, he will talk to us about the H0 and BAO tensions, the wXCDM, and dynamical dark energy in the late universe. Adrià, please start in your own time.
Okay, thanks a lot, Jackson, for the introduction, and I would like also to thank Eleonora and you for giving me the opportunity of presenting my work in this CosmoVerse seminar. So the outline of my talk is the following. So I will start in part one, discussing the existing tension between 2D BAO and 3D BAO measurements, okay, which is non-negligible. And of course, this has implications, right? Because BAO plays a fundamental role in building the inverse distance ladder. So using 2D or 3D BAO will lead to a completely different phenomenology required to alleviate the Hubble tension with late-time new physics. And this is what I'm going to present in the second part of my talk, proceeding in a quite model-independent way. Then in the third part, I will discuss the so-called wXCDM model, which I've developed here at the University of Barcelona with Professor Joan Sola. And I will compare the fitting performance of this model with lambda CDM and other well-known models in the literature like lambda SCDM model, the CPL parametrization, and so on. And in the last part of my talk, I will present a very recent work of mine written in collaboration with my PhD student, Alex Gonzalez, which is about the reconstruction of dark energy and low redshift expansion history using the weighted function regression method. So let's start with part one. This part is based on this paper written with Professor Marina Migliaccio and our PhD student Arianna Favale. It was published in Physics Letters B last year. And here we are going to quantify the tension between 3D and 2D BAO data. So I guess that for this audience, I do not need to remark the importance of the inverse distance ladder. I will do that very shortly. So you know that the BAO data is usually compressed in these observables, these ratios of the angular diameter distance and the moving sound horizon at the Baryon-Dirac epoch, or you can also, if you have enough information in the radial direction, you can obtain information on the dilation scale, and also on the product RD multiplied by the Hubble function at some redshift. Of course, if you want to infer pure low redshift information, you need to break degeneracy and provide a prior for RD. This is usually done assuming the standard pre-recombination physics. And if you use CMB data, you can extract this constraint on RD, use it as a prior, and combine it with BAO data to infer essentially measurements on the angular diameter distance, the dilation scale, and the Hubble function at several redshifts. Using more independent reconstruction techniques, you can reconstruct H of Z and extract an extrapolated value of H0 at redshift equal to 0. If you do so using anisotropic or 3D BAO data, it's very well known that this leads to low estimates of the Hubble parameter in tension we choose. But we will see in a moment that using 2D BAO data, things change. So if you want to build a tracer map in position space, you need to convert your observables, that is angles and redshifts, into distances. Galaxy surveys, of course, nobody knows which is the true model ruling the expansion of the universe. And galaxy surveys employ a fiducial model to do that, usually lambda CDM with some fixed parameters. They also use a template function that introduce other nuisance parameters, which are also fixed in the analysis. All these facts might introduce some model dependence in the anisotropic BAO measurements. And there are a couple of works by Anselmi and collaborators who showed that uncertainties in this 3D BAO analysis might be underestimated by a factor of 2, which is not a small amount. On the other hand, it's also possible to extract BAO information without having to convert redshifts into distances in the so-called angular or 2D BAO analysis. Okay, the methodology was proposed by Ariel Sanchez and collaborators in a paper that appeared in the archive in 2011. And essentially, you build shells in redshift space, and you compute the angular two-point correlation function. Of course, these shells have some width, so there are projection effects that should be corrected using MOX. But this method, in principle, should be more model independent. The thing is that although the 2D BAO data and 3D BAO data are obtained from the same or very similar catalogs of tracers, they lead to some different results. Okay, and this can be visualized in this plot. This theta is RD divided by the angular diameter distance at different redshifts. The solid line is the best fit lambda CDM model from Planck. And you can see here the 3D BAO data from BOS and also from DESI data release 1 seems to be in accordance with the standard model. But if you repeat the exercise with the 2D BAO data, these points fall above the best fit lambda CDM curve. Okay, so this is already telling us that there is a tension. And this tension was already, let's say, pointed out by David Camarena and Valerio Marra in 2020. But here in this paper, we wanted to quantify it in a model-independent way, and also independently from the calibrators of the distance ladders. Okay, that is independently from the calibration of supernovae of type 1a, and also independently from RD, the value of RD. So here we will quantify the tension between 2D BAO and 3D BAO from BOS, EBOS, and separately from DESI data release 1. How does the method work? So we have the angular BAO measurement on theta, okay, which depend on RD and DM, which is the co-moving angular diameter distance. And of course, for 2D and 3D BAO data, we have different redshifts. We have data points at different redshifts. So if we want to quantify the tension, we need to somehow interpolate between these redshifts, and we do so using supernovae of type 1a. Okay, under the assumption of the Etherington relation, of the validity of the Etherington relation, something that we have tested in our paper as well, and I will explain how in the next slide. Assuming the validity of this relation, we can express the product of calibrators of the distance ladders in terms of the BAO observable and the apparent magnitudes of supernovae of type 1a. So if we are able to reconstruct model independently the apparent magnitudes of supernovae of type 1a as a function of redshift, then we can relate the values of we can relate the BAO observations at different redshifts, and we can quantify the tension using this quantity. But of course, here it's important to test first the validity of the distance duality relation. We did so also model independently and independently from the calibrators of the distance ladders. And I'm just quoting here the results. So this eta parameterizes, let's say, the deviation or a possible violation of this relation. If it's equal to 1, there is no violation at all. And you can see that regardless of the of the BAO data that we use, 3D and 2D, or regardless of the supernovae sample that we employ in the analysis, we find only 1.2 sigma differences with respect to 1. So we find no hint of violation of the Etherington relation, and this allows us to apply the methodology that I was explaining in the previous slide. So the results are that the 3D and the 2D BAO data are in 2.5 sigma tension if you use Pantheon plus supernovae, okay? And this tension grows to 4.6 sigma if you replace the Pantheon plus supernovae with those from DES year 5, okay? So given this tension, it's of course interesting to see what are the phenomenological implications regarding the Hubble tension. Okay, this is a work that we did in collaboration also with Professor Jansen, which was published in PRD in last year. So we are going to focus on late time solutions. If we want to find a late time solution, we need, of course, to respect the very precise measurement on theta star. Theta star is essentially the inverse of the multiple at which we find the first peak of the CMB temperature power spectrum, and it is measured very precisely by the Planck collaboration, for instance, at 0.01% precision. Assuming standard pre-recombination physics is equivalent to say that the sound horizon and the decoupling time takes the same value or is constrained in the same way as in lambda CDM. So we need to also respect the lambda CDM constraint on the angular diameter distance to the last scattering surface. This means that if you modify the shape of the Hubble function at low redshifts in order to explain an increase of H0, you need to compensate that increase at higher redshifts by demanding lower values of H at earlier times. So the data that we employ is the following. We use shows prior on H0. We use CMB Gaussian priors based on lambda CDM on the angular diameter distance to the last scattering surface, on the sound horizon at the baryon drag epoch, and also on these two quantities, omega and tilde and H0 tilde, which I will describe in detail later on, but these parameters essentially control the shape of the Hubble function at high redshifts. It is okay to use constraints that come from lambda CDM, okay, because we don't expect variations of these quantities in the context of late time solutions. And of course, we combine this data with anisotropic or 3D BAO data or angular BAO data. Okay, so we do these two analyses separately in order to study the differences. So again, this is a very similar plot to the one I showed before, but in this case, I am already calibrating the BAO data using the value of RD from lambda CDM. Okay, and you can see here that the values of DA found in 2D BAO analysis are below the lambda CDM curve. So we expect deviations from lambda CDM at high redshifts if we want to solve the Hubble tension and explain this 2D BAO data. Okay, but what happens if we use 3D BAO? 3D BAO is in good agreement with lambda CDM. Here we use BOS and eBOS data because this analysis was previous to the DESI data release 1. But you can see here that the agreement is very good. And in particular, you have to be able to explain this very low redshift 3D BAO data point at 0.15. So you expect deviations from lambda CDM to enter at small or ultra small redshifts. Okay, and we will see that explicitly in the next slides. So we use the following fitting function. We assume the lambda CDM shape of for H at redshift larger than Z max, and we then consider some deviation entering at lower redshifts. Okay, this is just a phenomenological approach in which we consider two parabolae at redshift below and above pivot redshift ZP. And we, of course, impose some matching conditions in the boundaries. So you see here that there are many parameters, but you can reduce the number considerably by imposing these conditions. So at the end of the day, you have these extra parameters with respect to lambda CDM, omega m tilde and h naught tilde, which control the shape of the lambda CDM at high redshifts. And remember that we are imposing a lambda CDM Gaussian prior on these quantities. Then we have h naught, which will be essentially fixed by the Schuss prior. And then we have two additional parameters, set p, which is the pivot redshift, and the deviation from lambda CDM at this pivot redshift, which is delta HP. The methodology is very simple. We just fit the model to Schuss plus Planck plus 3D BAO on the one hand, and on the other hand, we replace 3D by 2D BAO. Okay, we perform a Monte Carlo analysis. We find the preferred shape of the Hubble function, and then we do another exercise. We say, okay, is this Hubble function compatible or consistent with a constant value of the absolute magnitude of supernova of type 1a? Okay, in principle, it should be, right? Because we are dealing with standardizable candles, supernova of type 1a. But if we find a deviation, this will mean that maybe we have some new physics entering at local scales. And this is what we want to test. These are the results obtained using 3D BAO. So you see here that, as expected, the shape of the Hubble function is very consistent with lambda CDM at high redshifts, and it has some departure, phantom-like departure, let's say, with a violation of the null energy condition below redshift 0.15, 0.2. Okay, so these curves are the 68% curves with lowest chi-squared in the Monte Carlo analysis. We do not find a lower bound on this transition, on this phantom-like transition. So in particular, we can have ultra slow redshift, ultra low redshift transition, sorry. And but the important thing here is that you do not only need a transition happening in H of Z, but you also need a simultaneous transition in the absolute magnitude of supernova of type 1a in the context of 3D BAO, right? At high redshifts, you find values that are consistent with, let's say, the value preferred by lambda CDM, minus 19.4. But then at some point, you need to enhance the value of M to the region preferred by Schuss. Okay, so this means that you cannot find a low redshift solution to the Hubble tension if you do not allow for new physics happening at local scales. As I've mentioned before, this can be translated. This increase in H of Z can be obtained by demanding a phantom-like effective dark energy density. And when I mean effective dark energy density, I mean that a modification of gravity or a combination of fluids or whatever it is in the dark energy sector. So these results are perfectly consistent with some others provided before us, like in this paper by Alestas, Kazantzidis, and Leandros Perivaropoulos in 2021, and also by Lavinia Heisenberg and collaborators in 2022. But here we wanted to remark the importance of having a joint transition both in H and in M. What happens if we substitute 3D BAO with 2D BAO? So in this case, we do not need to violate the null energy condition. Notice here that H dot, the derivative of H with respect to cosmic time, is still negative. The transition must be smoother in H of Z and M of Z. And actually, M of Z is compatible with the Schuss value in all the redshift range. Okay, so you don't need a transition in M. This is an important difference with respect to the results found with 3D BAO. And this departure from lambda CDM must cover a wider range of redshifts. And the important thing here is that if you want to explain the value of the Schuss observations, let's say, while respecting the good description of the other data sets, you need to have some sort of negative effective dark energy density at redshift larger than 2. Okay, this is another way of visualizing that the transition with 3D BAO data and 2D BAO data happen at very different redshift ranges. So now I want to discuss the wXCDM model, which I've developed with Professor Joan Solà in these couple of papers. The phenomenological description of the model is pretty simple. You have two components, one called X component acting at redshift larger than the transition redshift set T. This component has an equation of a state parameter, a constant equation of a state parameter, which is close to -1, but it has negative energy density, okay, and positive pressure. So notice that the behavior of this component that was coined in this paper of 2006 by Javier Grande, Joan Solà, and Stefancic was coined phantom matter, is very different from a phantom energy component, right? Because this component still obeys the strong energy condition. So in this equation of a state diagram, it lives in this triangle here, okay? So it still respects the strong energy condition, but it has negative energy density and positive pressure. And then below the redshift set T, at late times, we have a dynamical dark energy component, again, with an equation of a state parameter close to -1, but with the usual positive energy density and negative pressure. So, you know, this is positive, having this phantom matter component at large redshifts is positive. Why? Because you can compensate the increase of H at low redshifts that I was telling you before, okay? But apart from having implications at the background level, you also have some signatures at the linear perturbation level. And this can be understood very easily by looking at the question of the matter density contrast, okay? So you see here that dark energy contributes to speed up the universe and decrease the clustering. Why? Because you increase the friction term in the equation of the density contrast, and you decrease the Poisson term, okay? But what happens if you invert the sign of your component? That is, if you take a phantom matter instead of ordinary dark energy, okay, then it happens completely the opposite, right? The friction term decreases and the Poisson term increases. So you can have an enhancement of clustering before the transition where phantom matter dominates over ordinary dark energy. So this can have a bearing on or can provide a possible explanation of these James Webb Space Telescope observations of very large galaxies at redshifts between 5 and 10. This is something we have not explored yet, but we're planning to do that in the future. So there is a link to the theory, both for the dark energy part and phantom matter part. I provide here the references, but I will not focus on these aspects on this talk. So there is a resemblance with the very famous model lambda-S-CDM, okay? Although there are differences at the fundamental level. So in lambda-S-CDM model, you have a transition between an anti-de Sitter and de Sitter phase, okay, happening at a transition redshift set T. But here, the main difference with respect to the wXCDM model is that you allow for an extra dynamics, okay, both before and after the transition. And we will see that this has a positive impact when in the fitting analysis. Okay, we will see that in the next slide. So in the fitting analysis, we have employed this data. Okay, later on I will show some modifications of this data set, the results obtained with these modifications. But in the first table, I will show the results obtained with Planck 2018 CMB polarization, temperature, and lensing livelihoods, the Pantheon Plus compilation of supernovae together with the Schurz distance moduli, then cosmic chronometers, 2D BAO. Later on, I will show what happens if we replace this 2D BAO with 3D BAO, and then also large scale structure in the form of redshift space distortions. So these are the results obtained with these three models, the lambda-CDM, wXCDM, and lambda-S-CDM. The first observation here is that the value of H0 obtained in the lambda-CDM is higher than it's usually found with 3D BAO. But this does not mean that lambda-CDM is able to solve the tension, Why? Because the absolute magnitude of supernovae of type 1a still remains very close to the, very far away from the Schuss measurement. Okay, so this is only a mirage, let's say. There is no alleviation of the Hubble tension in lambda CDM, even if you use 2D BAO data. Okay. In the context of lambda SCDM and wXCDM, there is a clear alleviation of the Hubble tension. I exist in the context of 2D BAO analysis, and the values of M are perfectly compatible with Schuss. Okay, we find in both models a transition close to 1.5, and we find a 3 sigma evidence in favor of a quintessence-like evolution of dark energy at late times. Okay, and you see here that we can exclude lambda CDM very strongly, and there is still a gain in terms of minimum chi-square in wXCDM compared to lambda SCDM, and I will explain you why in the next slide. So if we analyze the individual contributions of chi-squared, we can see here that the gain in our model, in the wXCDM model, comes from the fact that we are able to improve by a lot the description of the supernovae data. Okay, and this can be seen, for instance, in this contour plot in the W omega m plane. So lambda SCDM is sitting here in the 3 sigma region, while in our model, due to the fact that we are allowing this additional freedom in the equation of a state parameter, we are able to sit within the 1 sigma region. Okay, so this is where this improvement comes from. And the situation with union 3 and DESIR 5 is this one. Okay, you find a similar effect. So we expect that if we replace Pantheon plus supernovae with DESIR 5 sample, we will find a non-negligible improvement. And this is what we show here in this table. We are just replacing. We are keeping 2D BAO, and we are replacing the Pantheon plus with DESIR 5 supernovae. Okay. Again, lambda CDM is very disfavored compared to these models. Here I also report the results obtained with CPL parametrization. We also find, let's say, a quintessence evolution, and then a phantom evolution. That is, we find a closing of the phantom divide, although the central values are quite different from those obtained with using 3D BAO, as I will show in the next slide. Okay. Notice that a simple dynamical evolution of dark energy is not enough to improve the description of the data. So if you use the wXCDM model, you obtain a minimum value of chi-squared, which is only marginally smaller than lambda CDM. So the real gain in terms of the information criteria comes if you allow for more freedom in the dark energy sector. Okay, and notice that as expected here, we are even improving with respect to lambda SCDM, the description of the data compared to the previous table. And what happens if we substitute the 2D BAO with 3D BAO? Okay, what happens? Here we are using 3D BAO from BOS and EBOS, not from DESI. Okay, and it's remarkable to find that the central values in the CPL parametrization for W0 and WA sit exactly as DESI is finding. Okay, notice that this analysis was performed some months before the appearance of data release to DESI data, and we're finding the same central values or very similar as those provided by DESI, even though we are not using DESI data. So this means that DESI data, does not play a crucial role in this story, in finding the signal in favor of dynamical dark energy. And we find that in the context of the CPL parametrization, we can exclude lambda CDM at 4.2 sigma. Again, I repeat, without DESI data. Okay. So when you add 3D BAO data as expected, we cannot solve the Hubble tension in any dynamical dark energy, late-time dynamical dark energy, as it was advanced in the previous slides in our phenomenological analysis. Okay. Despite this, it's important to pinpoint that the description of the data in terms of the wXCDM model is still pretty close to the CPL parametrization. Okay, and now I will tell you about this analysis that appeared on Monday in Archive. This paper has been written with my student Alex Gonzalez Fuentes, and it's about the reconstruction of dark energy and cosmographical functions using weighted function regression method. So what is the motivation? So, you know, the evidence for dynamical dark energy is usually quantified using the CPL parametrization. Okay, this is what, for instance, the SE collaboration has done, and they find a level of exclusion of 2.8, 4.2 sigma, depending on which supernova dataset you use, Pantheon Plus or the SGR5. Fine, but what features of the best fit CPL parametrization actually lead to such improvement in the description of the data? This is an important question. And in a recent paper by Savas Neseris, Yashar Akrami, and Glenn Starkman, they showed that, for instance, if you use higher orders in the Taylor expansion of W of the equation of state parameter, for instance, if you consider a parabola instead of a linear relation, or if you use a cubic expansion in the so-called CPL plus or CPL plus parametrizations, then you find some differences. For instance, you find that W0, that is the equation of the state parameter at redshift equal to 0, departs from -1 at a much less statistical level. Okay, so you only find a 2.5 maybe departure from -1. Okay, even though you still find some evidence of phantom crossing divide. So it's very important to pinpoint, to identify which are the characteristics that are actually leading to this improvement in the description of the data. And in order to do so, we need a model-independent reconstruction methods. Okay, so sorry. This method, the weighted function regression method, was developed in these two papers in 2018, in which I applied it to the reconstruction of the Hubble and deceleration parameters using low redshift data from BAO, supernovae, and cosmic chronometers. But we have applied it for the first time in the reconstruction of the dark energy properties. This method works as follows. Instead of using only one particular parametrization of the equation of state parameter, for instance, the wXCDM or CPL, we use effectively all the information contained in every truncation order. Okay, and then we build a joint probability distribution using Bayesian weights. Okay, so we made here a simplification. Instead of using the full Bayesian evidence, we estimated the Bayesian weights using the Akaitin information criterion, okay, which simplifies the analysis a little bit. I mean, if we did not do that, then the analysis would be much more expensive from the computational point of view. And we applied these 3 steps, very simple. First, we fit all the models, MJ, where each value of J is linked to a particular truncation order of the equation of a state parameter. Then we compute the weights. Then we build the weighted probability density, and we use this weighted probability density to reconstruct the quantities of interest. Okay, in such a way, we are not making subjective choices. We are not selecting just one truncation order. We are using the information contained in all the possible truncation orders, and we are asking the data which is the preferred, let's say, effective number of parameters entering the reconstruction. Of course, there is still the freedom of choosing the basis, and we have to show that the result is not dependent on this specific choice. Okay, so we explored two different bases, the so-called W basis, in which we include the wCDM, the CPL, CPL+, CPL++, and so on. And it's possible to obtain an analytical form of the dark energy density for each model contained in this basis. It takes this cumbersome form, and then, but still it's analytical, so it's fine. And then we have the raw basis. Okay, why do we consider this basis? Because the raw base, the W basis, does not allow for negative energy density. So if we want to assess if negative energy densities are preferred at large redshifts, we need to allow for this additional freedom. And we can compute also analytically the equation of a state parameter associated to these models. Okay, notice that we can have zeros in the denominator which are linked to the transitions from positive to negative energy densities. Okay, these zeros are the same ones that are encountered here. Okay, so these are the plots that show the equation of a state parameter and the normalized the energy density as a function of the redshift for the individual models entering the basis, the W basis and the rho basis, using this year 5 supernova data and Pantheon plus data. Okay, and you can see here that okay, wCDM. I mean, once you allow for additional freedom to the model, you rapidly go to values to behavior of phantom of crossing of the phantom divide. Okay, so notice that in the CPL, CPL+, CPL++, and also in the various truncations orders of in the raw basis, once you allow for additional freedom, you have a transition from quintessence to phantom at large redshift. Okay. Now we have to use all this information to build the reconstructed or the weighted probability density. And with this reconstructed probability density, we build the final reconstruction of the various cosmological functions of interest. Okay, see here that we are also plotting the Hubble function and the deceleration parameter and the jerk. Okay, so at large redshifts we have something that is compatible with lambda CDM, but below redshift 1.5 we have some departure in the deceleration parameter and also in the jerk, although of course the jerk is much less constrained. Okay, these results are fully compatible with those provided by Loda et al. In this DESI paper, sorry, are fully consistent, but here we are using different data sets, a different statistical technique, and we are proceeding in a fully Bayesian way, in the sense that we do not have to fix the order, the truncation order of the reconstructed function. Then we also quantified here the probability of crossing the phantom divide. Okay, using okay, all these results are obtained also using DESI data, data release 2. So using this year 5 supernovae, we find a 99.97% probability of crossing the phantom divide. This crossing happens at redshift 0.4 plus minus 0.1, and the effective number of parameters entering the reconstruction is 2.46. Okay, this can be all the details are provided in the paper. This is just a short summary. Then when you substitute this year 5 with Pantheon Plus, you can see here that somehow the evidence decreases. In particular, the value of W0 at redshift equal to 0 becomes compatible with -1 at 1 sigma. But still, you have a large probability of crossing the phantom divide, which stays at 98.88% using the W basis. And with the raw basis, it's also high. It's 96.21%. Okay, the results using the raw basis and the W basis are very similar, but here in the raw basis we're allowing negative energy density states, and this makes this tail to go a little bit lower. Okay, and in fact we can quantify the probability of having negative dark energy between redshift 0 and redshift 3, and it's of 2.32%. Okay, we have to bear in mind that these results are obtained using 3D BAO. If we did that exercise with 2D BAO, probably we would obtain a much larger probability. Okay. So these claims for dynamical dark energy are not the first ones, okay, that appear in the literature. There have been several papers advocating, the finding hints of dynamical dark energy in the past, and it's good and positive, healthy, and fair to acknowledge all these previous works. Of course, the origin and implications of these findings might have changed because data have evolved, let's say. But as I say, I think that it's good to at least show some of the papers that found already, 10 years ago, some hints in some data sets for dynamical dark energy. And let me go to the conclusions. So I've started this presentation remarking the importance of the inverse distance data. Of course, it plays a very important role in the discussion of the Hubble tension. We have seen that 3D and 2D BAO data are in tension between 2.5, 4.6 sigma tension, depending on the supernova sample that you employ to perform the interpolation between the BAO redshifts. And this has implications regarding the possible solutions to the Hubble tension at late times. Using anisotropic BAO data requires a very low redshift departure from lambda CDM, happening at redshift lower than 0.15. You need an effective phantom behavior of dark energy with a simultaneous transition in M, okay, which perhaps is not a very natural solution, and this is why people have explored also the possibility of solving the Hubble tension with pre-recombination physics. And angular BAO allows you to solve the Hubble tension without the need of modifying M. You can explain the data keeping the value of M measured by shoes. Okay, and in this case you need negative dark energy density at redshifts 1.5 or 2. Okay, we have seen that wXCDM model solves the Hubble and group tensions when 2D BAO is employed in the fitting analysis. And it's also able to improve the description of the supernova data compared to lambda SCDM. And this explains why the former is strongly preferred over the later. This in the context of the 2D BAO. In the context of the 3D BAO, no model, no late time dark energy model can solve the Hubble tension, and this is a factual reality. Although the wXCDM model can still offer a good description of the cosmological data comparable to the one offered by the CPL. And in the last part of my seminar, I have advocated the use of model-independent techniques to reconstruct the dark energy properties and also to reconstruct cosmographical functions in the late universe. This technique, the weighted function regression method, allows us to perform these reconstructions with a very good control of the effective number of additional parameters. This is something that might not be the case in with other methodologies. For instance, with splines, you have to select the number of nodes and so on. It's important to keep the number of additional parameters under control when you perform reconstructions, because otherwise you could incur in overfitting issues. And this method has allowed us to pinpoint some of the important dark energy features preferred by current CMB, BAO, and supernova data. We have quantified the probability of crossing of the phantom divide. And of course, and I think this is important, for a correct assessment of the true level of evidence for the dark energy dynamics, it will be of utmost importance to understand the impact of systematics in the supernova samples, because we have seen that the results depend a bit on what supernova sample you choose to reconstruct the dark energy properties, and also in the shoes measurement, okay, because this dynamical dark energy cannot solve the Hubble tension in the context of 3D BAO. And if the shoes measurement is correct, it's not affected by important biases, then we should reassess the level of evidence in favor of dynamical dark energy. And that's all. thank you very much for your attention, and I will be pleased to take questions.
So thanks so much for a very interesting talk. In fact, there are already some questions. I would say let's start with Simone, because she put some comments earlier on, and then Pieros, who just raised his hand. Simone, I don't know if you want to unmute and say the question you have in the chat. No, okay. Adrià, I mean, I can read it.
Oh, okay.
Oh, yeah, you can see it as well. I mean, so in the first one, she's talking about the DAISY 5 having eta, yeah.
Yes,
Equals one deviation.
Okay. Let's show again this slide. So
Yeah.
I guess that she's talking about this plot. So with this year 5, yes, but we have to bear in mind that this is a 1 sigma band. Okay. So this means that at 1.2 sigmas, I was telling you before, the value of theta is compatible with 1. So there is no statistically significant deviation from 1. There is no hint of a violation of the Etherington relation. We have not found this hint. It's true that we have proceeded in a model-independent way, and independent, I mean, our analysis is independent from the calibration of the distance ladders. No? So this might make the error bars grow a little bit, but yeah, we don't find a deviation from the distance duality relation.
Then I think Pieros had a question. Next.
Yeah, thank you for the very nice talk. I have 2 questions. The first one is about the interpretation of the phantom matter.
Okay.
You said this has negative energy density. So does that mean it behaves like antimatter since it has negative energy, or behaves some what you call phantom matter because it is positive energy but in some kind of negative volume?
Good question. Actually, this phantom matter component is quite exotic. Okay. Well, in some sense, it works at least at the level of linear perturbations. It works as more or less as ordinary matter, let's say, because it helps to have more clustering in the universe. Okay. So this negative energy density and positive pressure are helping to make a structure to collapse more efficiently. So I don't know if this is aligned with your concept of antimatter. No, at the level of perturbations, I would say that it works more like ordinary matter. Okay. But of course, it introduces important differences in the Friedman equations. Okay. So I would say that yeah, I recommend you to read these references for more details. So the existence of phantom matter like of a phantom matter like component has been shown to be possible in the context of inflation, for instance. Okay, when you approach a de Sitter phase, like happens in some inflationary era, or could happen nowadays because it seems we are approaching a new de Sitter phase. So this phantom matter effective behavior could arise from a combination of effects, okay, that appear when you approach a de Sitter phase. And this has been shown in the context of inflation, which of course involves a completely different energy scale, but we just explore the phenomenological implications of this type of matter in the late universe. Okay. Yeah, I don't know if this answers your question, more or less.
Kinda, yeah. So I will read more, and if there's time for one more fast question.
Okay, yes, fast.
On slide 9, you were showing the relation between RD bar and theta, which is a ratio. Yeah.
Yes.
So RD has units of distance and theta is a ratio. So is there a missing unit somewhere? Maybe.
RD has units of distance and DM has okay. Yeah, I see here in this formula, right?
Yeah.
Okay, yes, because I'm sorry, I have not said that, but this RD bar is the dimensionless comoving sound horizon. So this is RD divided by 1 megaparsec.
Okay, thank you.
Thanks.
Perfect. I think Sayanta was next.
Yeah, actually, I will not take much. So I'm just asking that what you have analyzed in DAISY data, etc. It seems like, as you said, that it is not favoring like dynamical dark energy, etc. So I'm asking like in two sense. First, like as the quintessence or even in string theory, the tachyon modes are very popular. So I'm asking that how would you like then answer the cosmological constant problem? Like there has to be some mechanism to make it lower, etc. So I understand it is a like observational work, but I'm just asking that. Is there a way forward after your conclusion? Like what should we do? One should only stick to lambda CDM, or if somebody takes a scalar field, it gives a more tighter constraint on the slow roll parameters or something like that. So I'm just asking. Thank you.
So I'm not sure if I understood correctly the question. Are you referring to the results shown in the last part of my talk?
No, I am asking in general. Suppose I am working on a scalar field, say quintessence model, whatever it is, or some phantom scalar field model, and I am, as you know, that we'll get dynamical dark energy. The cosmological constant decays very slowly. As the DAISY data are showing, like the dynamical dark energies are not very favorable. So I am asking that how should one proceed? I mean, one should stick with the cosmological constant.
I would say that this is favoring dynamical dark energy, right? But it's not favoring a very simple form of dynamical dark energy. Look, this is the normalized shape of the dark energy density. So you need a quintessence behavior below redshift 0.5, and then a kind of phantom behavior at larger redshifts. Okay, so the quintessence part could be explained in the context of running vacuum models or or scalar field. I mean, generating this quintessence kind of behavior is relatively easy. The difficult part comes from here, no? But I mean, although I'm talking about dark energy, here we have to understand that this reconstruction is actually it could be many things. You know, inside this box of dark energy could be modified gravity mixed with a scalar field, other scalar fields, and I mean it can be highly non-trivial. Okay, this is the form of the dark energy, effective dark energy, that is not containing the dark matter part and the baryonic part. Okay, this is how we have to interpret this plot.
Yeah, actually, I am asking in the context of Anjanananda Sen itself. I mean, he is proposing this type of thing, like where the kinetic term changes the sign. I mean, it can naturally go from quintessence to the phantom in some string vacuum model, like some moduli space, etc. So that's what I am asking, that if certain things happen, I mean, as the data shows, I mean, just like in potential, we have a very tight constraint on the slow roll parameters, like I mean, epsilon and epsilon 2. So I'm just asking that, is there a very tight constraint on the kinetic switching, like when this happens? Like, is there a data or some analysis has been done? So in that case,
I don't know. I don't have an answer to this. But what I can tell you is that a combination of quintessence and phantom cannot explain this. This shape cannot be explained by a combination of phantom and quintessence. So if you combine a quintessence and a phantom fluid, you can produce a transition from quintessence to phantom, but not the other way around. Okay. So whatever it is, it has to be something more complicated, which might involve modified gravity or I don't know. This is something that I have to explore myself.
Sure. Thank you very much, sir. Nice talk.
Thanks.
Thank you. I think Kushal.
Thank you for the nice talk. There are many things that I disagree with here, but I will restrict my question to the second part of the talk. Have you tested any of these things with mocks? Because any parameterization is highly sensitive to what you do. If you want to have a look, we have an appendix in the dark energy supporting paper where we test a thawing quintessence model and try to reconstruct with GP and all those things. And we see bias, right? So any comment about detecting phantom crossing is just very difficult to sell in my principle. And the second question that I have is that when you are adding these weights, you are considering AIC. AIC does not take anything into the account, the fact that how much data is constraining. So the fact that you are doing this CPL++ and all those things, those parameters are not constrained at all with data. So you are adding them, you are downweighting them with some factor, but that really doesn't tell you how much your data is informative on this posterior, like on these parameters. So I am not entirely sure about, and although you do say that the results are consistent, I see that if I look at the H by H lambda, that is obviously not consistent with what we see in the DAISY. So I would like to hear your comments on this.
So, sorry, you mean this plot?
Yes.
This is consistent. I mean, this makes perfect sense. First, because if you need if you increase the amount of dark energy in the late universe, and if you want to keep the good description, I mean, to explain the measured distance to the last scattering surface, you need to produce lower values of H than in the lambda CDM. So I don't know what you obtained in your DESI paper, but these results make perfect sense. The H lambda function here is obtained using the best fit Planck lambda CDM analysis. Okay, it's not obtained from the fit to these data sets. So we are comparing because in the context, if you use lambda CDM, there is some tension with if you perform the analysis with this data. Lambda CDM is not able to explain all the data sets together in a successful way. So we opted to use the best fit lambda CDM model obtained from CMB analysis, which is a kind of purer estimate of H in the context of lambda CDM. So this shape, I think it's perfectly consistent with our expectations. Regarding AIC, we are fully aware that the cake information criteria is not the, let's say, the most precise way of computing Bayesian evidences or estimating them. But as I've said, it was a way of simplifying the computational analysis. We are planning to improve this part, applying a methodology, another methodology that was developed actually by Luca Amendola recently. But of course, we will have to do that without using the full CMB livelihoods, because it's, I mean, I don't know, maybe you have a supercomputer, but in my case, I do not have a supercomputer, and we have to choose, right? But we are planning to improve this part of the analysis. But what I can tell you is that we obtain consistent results with also when we change the basis of our reconstruction method. Okay, and if you go to our paper, you will see which is the weight for each truncation order in the expansion. Okay.
I think in my experience, I noticed that once you start including this higher order terms, you do not even get, you do have a bias in your inference. So for example, what you can do is that you can create a MOX. You can choose any fiducial W of Z that you want. Do not introduce any noise into the data. So like these are noiseless MOX that you can create. And then you can run your pipeline and check whether you do see a bias or not.
Yeah, but imagine this. Sorry. Yeah, please go ahead.
Did see the bias, and this is one of the reasons that even in our last year DR1's crossing statistics, which also does a polynomial expansion kind of a thing, we had to put some kind of a Gaussian prior, because if you just put a flat prior on this extended parameter space, you will incur a bias, because once your equation of state becomes phantom, then it's not affecting your any observables at all at higher redshift, because in H square, the contribution is mainly coming from the omega matter. So in that case, there is this.
Yeah,
kind
of course, these
Isolate.
reconstructions are only reliable up to redshift 2.5 or so. So whatever happens
you
larger
can look at-
redshifts, then you cannot rely on that.
You can calculate the matter dark energy equality, and you will realize it's not even 1, right? So anything after 1, we should not be able to say anything conclusively about it.
Okay, that's your point, but I think that we could be here discussing forever.
Thanks you once again for a very nice, interesting talk.
Thanks a lot.